Today, what we're going to be doing is we're going to be starting our POGL on mechanical energy. So mechanical energy is going to be what we're looking at for the next few weeks. I think it's the next 3 weeks or so. And so for mechanical energy, what we're going to be doing is we are going to actually look at mechanical energy and spring energy now. And then we're going to focus on mechanical energy first, and then we're going to look more into spring energy afterwards before that test comes in where it covers everything from work, power, and energy. So if you guys open up your assignment for today, I do want to go through the first one as a class just to kind of bring our heads back into this work and power space. So it says that remember that work and power POGL that work is done when a force moves an object some distance. When work is done on an object, that object increases its energy by the same amount. So we're going to consider the situation in a frictionless box being pushed up a ramp. The work done on that box depends on the force applied and the distance the box is pushed. To move the box at a constant velocity. The applied force will equal the force of gravity in the x direction because that object has a constant velocity, because that object has a constant velocity, it's not accelerating, meaning that all its forces in the x direction have to equal one another because there's only those two forces, which means the force of gravity in the x direction equals our force applied. And we're going to assume for the situation below that it's a 1 kilogram box and it's being pushed up the ramp that has a height of 2 meters. And we're calculating that work done. All right, so if we do this first one together, a couple things we have to remember. It has a constant velocity. So we need to first draw the free body diagram of this box. So what forces do we have on this box?
Gravity.
Gravity, perfect. So we have gravity. And which way does gravity go?
Down.
Down, perfect. Yeah, gravity going down. F, G. What other forces do we have?
Normal force.
Is that normal force? Where does that one go?
Up.
Up, perfect. Going perpendicular to our surface. So the normal force. And what other forces do we have?
Applied force.
We have an applied force pushing that box up the ramp. Awesome. Any other forces? All right, and then we have to draw our components because it says include those components of the forces, which means we're going to draw the components for which force? What force is going to have components to it?
Gravity.
Gravity, perfect. So let's draw those components. FGY and FGX. So it tells us up above that our force applied is equal to the force of gravity, but let's just double check. So we know our object is going to be moving in this direction. It's going up the ramp, which means that which direction is that? Is that the x direction or is that the y direction?
X.
It's the x direction. So we know our force in the x direction is what we're looking for. And we also know that it's going up the ramp with a constant velocity. And if we have a constant velocity, what does that tell us about our force in the x direction overall? Or what does it tell us in general if we have a constant velocity? Any ideas? All right, let's be more specific. What does it mean to our acceleration if there's a constant velocity?
Is acceleration 0?
Acceleration is 0. So if our acceleration is 0, that means when we do mass times acceleration, find our force in general in the x direction, that force of x is going to equal 0. So there's no force, or there's no change in force in the x direction, which means that if we look at all of our forces in the x direction, which forces do we have if we're adding up all of our forces? What forces do we have in the x direction?
The applied force and the force of gravity in the x direction.
Right, we have those two forces. And so are they going in the same direction, or is one of those going to be negative because it's going in the opposite direction? Are they adding together? Are we going to subtract them? What are we going to do?
Subtract the force of gravity.
We're going to subtract these two because this one is going the opposite way of our motion. So it's a negative, just like work done on the object is negative when it's going the opposite direction of our motion. So is our force. So if we know this, the sum of our forces in the x direction equals the applied force minus the force of gravity. And we know that the sum of our forces, or our force in the x direction overall, has to equal 0. What can we do with this right here? What can we set it equal to?
Isn't it just 0?
It is just 0. So we're saying equal to 0, which means when we solve for our force applied, it's just going to equal our force of gravity in the x direction. All right. So now that we've seen that, we know this happens. Force applied equals the force of gravity in the x direction. We need to be able to figure out our force of gravity in the x direction. So how are we going to find just that force down here? How are we going to find this bad boy? Do we know how to find anything on that triangle? Sine, awesome. We're going to use sine because we do know this angle right here. That angle is going to be what value?
30 degrees.
30 degrees, perfect. This is the 30 degrees right here. If you drew your triangle the other way, so I'm just going to change colors real quick. If you draw your triangle going this way, I just want you to be aware that the angle comes down here for that one. It's not also up here. So just so you're aware, because I know people do it both the ways. So just making sure you guys know, if you're drawing it that way, your angle does go in the bottom right corner, not the top left again. All right, so I'm going to continue looking at just that purple triangle, and we know that sine of theta equals what divided by what? What's the sine of theta equal to? How do we find sine? If we're doing our trig function, sine is it opposite adjacent or hypotenuse divided by opposite adjacent or hypotenuse?
It's opposite over hypotenuse.
It is opposite over hypotenuse, which means it is force of gravity in the x direction over what, Saul?
Over the force of gravity.
Awesome. All right, so now if I wanted force of gravity force of gravity in the x direction by itself, what would I have it equal to? How can I get that all by itself?
You multiply the force of gravity to both sides.
We multiply that force of gravity to both sides. So this goes away. So we know the force of gravity in the x direction equals the force of gravity times the sine of theta. All right, one more quick thing to remember. How do we find the force of gravity? Just in general, how do we find that one? Can anybody tell me that equation to find the force of gravity? All right, we have the acceleration. All right, what about the acceleration? What are we going to use with that acceleration? How do we find any force? How do we solve for any force?
Usually mass times acceleration.
Mass times acceleration. And then do we know anything specific about gravity?
The acceleration of gravity.
Awesome. We know the acceleration of gravity is g, which is 9.81 meters per second squared. So what we're going to do is we're going to replace this one more time. Our force applied, we know, is equal to both those things, but we're going to replace Fg with the mass times the acceleration due to gravity times the sine of theta. Now, we have each one of those things. We know the mass from up here is 1 kilogram. We know that the acceleration due to gravity is 9.81 meters per second squared, and we know the angle is 30 degrees. Now all we have to do is plug in and solve. What are we going to get for our applied force?
I got 4.9.
4.9 newtons. Anybody else get 4.9 newtons?
I did.
Woo! There we go. We're perfect. All right, so we know our force applied. Now we have to figure out the distance. So how are we going to figure out the distance of this object traveling? Which one of these sides is going to be our distance that we want to figure out? The 2 meters, the base, the hypotenuse, the height. Which one? Which one of those is going to give us our distance?
The adjacent length to
Yeah.
30.
The adjacent length. So the base or the hypotenuse?
The base.
Base. So that one down there?
Yeah.
All right. Everybody agree? All right. I got lots of thumbs up. Somebody else was saying something else? Somebody else say something? All right. I am going to say that we're
Wait,
going to.
wouldn't it be the hypotenuse?
It is going to be the hypotenuse for that one. So we actually want that hypotenuse, that long line, because that's where our box is actually going up. The base doesn't give us that whole thing. The hypotenuse is going to give us the whole thing. So how do we find that length? How are we going to figure that one out? Sine again, awesome. So we have sine is of theta equals, we said it was opposite, whoops, that's an A, opposite over hypotenuse. And we know that the angle is 30. Ooh. Equals opposite. What is opposite of our angle?
Two.
2 meters, perfect. Over our distance. So our distance is going to be just labeled D, just because that's the variable we need for our work equation. So how do I get D by itself? Multiply, perfect. So I'm going to multiply both sides by D. And it goes away here. So now I have D sine 30 equals 2.0 meters. How do I get D by itself now? Divide, perfect. Well, what were you saying?
I was gonna say the same thing.
Awesome, sweet. So we're going to divide both sides by what value? Are we dividing by the sine of 30 or 2?
Sine of 30.
Awesome. We go away here. We're left with D equals what value? What is 2 divided by the sine of 30? It is 4. Perfect. All right. Last but not least, how do we find work?
Force times distance.
Force times distance, and we have both those. We know it was 4.9 newtons times the 4 meters. And what is our work? All right, 19.6 joules. And then how many sig figs do we care about? 1, 2, 3, 4, 7, 12. 2. So I also heard 20 joules. Or you can put that bar up above. Either way, we have our answer for work. We crushed it. And this should look very similar to the lab you just did yesterday and Tuesday, since you did the same thing just with your body instead of a box.